Hi, everybody. Wait, no, this is really loud. So welcome back. We have two more talks. And right now, I would like to introduce Dr. Desai. She's coming from UC Davis, and she's going to be talking to us about climate change and emerging infectious diseases. Dr. Desai?
Thank you so much, everyone, and thanks for the kind invitation to come speak with you all today. I do have to caveat, I'm towards the end of my maternity leave right now, so if there's any moments of incoherence, please forgive me and feel free to call me out on it. So I'm really excited to be able to talk to you today about emerging, and I've put in parentheses because I think a lot of what we're going to talk about is really this idea of infectious diseases that we already know that are endemic in certain areas, and kind of looking at the associations of how extreme weather events may ultimately prove to shift that existing epidemiology outside of traditional regions that we've known certain infectious diseases and communicable diseases to exist. So I have no relevant disclosures. And so I've got three objectives for this talk. So I'm going to talk to you a little bit about just sort of the changing epidemiology in general related to climate change. I'm going to present a lot of data that is available on the association of extreme weather events, climate change, and infectious diseases. And then I'm going to show a few case studies that try to exemplify these associations. So to start, we'll talk a little bit about the epidemiology. I realize this is a terrible slide. There's so many words on it, and it's a table, which I feel like we try to avoid. But I put it up here because I think it's a really well done table, and it exemplifies, I think, the challenges in trying to really quantify these associations, right? Trying to really understand and get at the impacts of climate-related changes on infectious diseases. And I think a lot of that has to do with the fact that much of the data, and even the data that I'm going to present today, has really relied on predictive modeling, because we don't exactly have great ways to quantify some of these effects. And so a lot of it really does rely on spaces where, a lot of this is, all of this is really observational. We know that there are effects that are occurring, but I think we're still trying to kind of get our minds around how we can best really explain and depict these phenomena. So this is a table from a perspective piece in JAMA. It was published last year. And they kind of try to look at different disease types and how potential climate-related changes or extreme weather events might ultimately impact the epidemiology. And so if you look at vector-borne diseases, for example, they talk about evidence that looks at shorter, warmer winters, longer summers, and how this could increase disease incidence, expand geographic ranges of vectors, we'll talk about that a little bit later, and also increase the likelihood of onward transmission. They also look at zoonotic diseases and the ways in which extreme weather events can change animal migration patterns and population density. It can also lead to land use changes and habitat destruction, thereby increasing the interaction between not only different animal species, but human and animal interactions, which of course increases the risk not only for cross-species transmission events, and I have a paper here that's going to talk a little bit more about that in detail, but also the risk for spillover. It also talks about fungal diseases, and really how expanded thermotolerance in fungal organisms. As we all know, fungi are very uniquely sensitive to temperature, and some of the ways in which warmer climates can potentially provide favorable environments for endemic fungi, thereby not only leading to the emergence of new pathogens, but also expanding the geographic range of endemic mycoses. And then they also talk about waterborne diseases. And so, flooding, for example, changes in precipitation patterns, and how we've actually observed already increased disease incidence after storms. So these are, isolated events, but maybe provide some evidence of what could be to come with larger events related to climate change. And again, expanding the geographic range of these organisms as well. And so, the authors here conclude that these changes may alter infectious disease epidemiology, not only in the US, but internationally, as traditionally accepted regions of disease acquisition lose relevance, seasonal associations change. So all of the things that we're taught about epidemiology with communicable diseases may be changing. And also how all of these events may provide good fodder, or new fodder, for novel pathogens to emerge. And so let's drill down a little bit more discreetly on some of these pathogens. I'm going to start with zoonoses. And so just taking a step back, thinking about emerging infectious disease events in general. So this is a very well-known paper. It's pretty old now. It was published in 2008 in Nature, but it was really one of the first attempts to try to characterize sort of the trajectory of the emergence of novel pathogens, and particularly among humans. And so they included newly evolved strains of known pathogens, but also pathogens with recent emergence among humans, and pathogens with recent increased incidence. And they looked at the literature from 1940 to 2004 and identified over 300 emerging disease events in humans around the world. And they found that over time, even when they controlled for increased reporting, that there has absolutely been an increase in the number of emerging disease events since that time, since 1940. And the majority of these events, 60%, 60 to 70% really, if you look at the data across the board, seems to be caused by zoonotic pathogens. And most of these, so 70% of these events among zoonotic pathogens were caused by pathogens with a wildlife origin. And they also found that the number of emerging disease events caused by pathogens originating in wildlife have increased significantly over time. So of course, the question here is why? And I think this image kind of explains the chaos a little bit in trying to really determine what the reasons are. And as with many things in infectious disease, the answer is it's multifactorial. But I know there were some great talks earlier today kind of focusing in on the One Health approach. And I think this is a really good case study for considering the One Health perspective and its sort of framework for thinking about emerging infectious diseases, specifically zoonotic pathogens, and its relationship with climate change. And so what this paper tries to do, it's a bibliometric analysis, and it really looked at all of the factors that go into zoonoses and zoonotic pathogen emergence, specifically viruses. And they hone in on factors such as urbanization, deforestation, environmental change, so all things that bring animals and different animal species and also animal and humans closer together in closer contact, thereby increasing the risk for potential spillover events. But they also talk about environmental change and climate change as part of this. And I think this is one of the reasons why it's a little bit challenging to really be able to attribute how climate change uniquely impacts disease incidence and changing epidemiology, because it really is part of a larger structure here of events that are driven by human behavior primarily, that are kind of resulting in changes that we're seeing. But this is a paper that really tries to look at the emergence of zoonoses, novel zoonoses rather, and looks at climate change as one of the factors. And so some of the thoughts posited here are that climate change drives range shifts for reservoir species, and so that leads to pathogen emergence. It affects transmission and susceptibility, and so that affects disease dynamics. And then it affects the geographical range of vectors, and so that leads to global spread. But you can see here they also talk about things like technological change. So transportation is a huge one. We're able to go, I don't think I put this slide in here, but there's a great review paper that has an image of the ways in which global transportation have changed over time and kind of correlates that with how specific infectious diseases have spread. And you can see that because we can get from one side of the earth to the other in a day, that the ability to transmit pathogens and for people to come into contact more readily has really certainly affected the way in which disease is spread. And then, of course, demographic changes, so population growth, urbanization, and aging. But of course, this is a talk about climate change, so let's talk a little bit about how climate change has been posited to create more pathways for zoonotic disease transmission. Okay, good. I'm glad the screen is so large, because I've got a lot of these figures in here, and I want to make sure you'll be able to see it. But so, we have higher temperatures, rainfall variability, high sea levels, storms, floods, droughts, wildfires. So how does this affect zoonotic disease transmission? Well, as I've mentioned already, direct contact between species increase. The geographic ranges of host animals and insects change. Something we haven't mentioned quite yet is that disease hosts also thrive in more favorable conditions. So an example of this would be heavy rainfall can lead to increased vegetation in certain areas, which allows host animals, such as rats or other rodents, to reproduce more readily. And when you have the host, then you have the possibility for that disease to be able to potentially transmit more readily among humans. You also have human resistance disease. So something we don't talk about a lot when we talk about things like extreme weather events and infectious diseases is this idea that exposure, right? So things that happen to the host in this case being humans. So extreme weather events such as heat, for example, can exacerbate chronic disease or chronic illness, making it harder for an individual who's already susceptible to be even more susceptible or vulnerable to communicable disease or infectious disease. So what's the evidence here? This is all of these things have been posited. As I said, a lot of this relies on predictive modeling, and so this is a paper that tries to do just that. So this was published in Nature a few years ago, and what the authors here try to do is look at how climate change and climate-related factors specifically may affect the transmission risk of certain zoonotic viruses. And so they look at climate at a variety of different levels and parameters. And what they found here is that over time, so over a 40-year period up until 2060, they predict that with climate shifts, animal species may aggregate in new combinations. So we may see different species that wouldn't have necessarily been in contact previously, driven by climate, related migration or pressures. Obviously they themselves carry their own risks of certain zoonotic viruses. They come together, then you may have a new combination or the potential for emergence of a new pathogen. And I think the thing that's kind of interesting about this study too is when they look kind of retrospectively, they posit that this ecological transition may already be underway. We're already seeing the effects of some of this. And there's some evidence to suggest that this is just going to continue thereafter. And so I told you I was going to have a couple of case studies. So this is one from a paper that looked at the impacts of a few different factors, but included environmental factors on the emergence and epidemic potential of Ebola, and specifically Zaire Ebola virus in Africa, in West Africa. And so they, again, tried to look at the changes in future risk of Zaire Ebola virus into 2070, so from present time to 2070. And what they found is that country-level patterns showed a trend of general decrease in the risk of Ebola virus disease for better case scenarios. So countries, and specifically, again, they were focusing on West and Central Africa, but countries that had a high level of climate mitigation strategies or policies seemed to do better in terms of their potential to have a risk of these explosive outbreaks or spillover events related to Ebola virus disease. This is compared to countries that have, this is the worst case scenario, countries that maybe don't have these policies or procedures in place or plans in place, and they tended to do much worse. So I think this is fairly intuitive. But what they do find also is that overall outbreaks are likely to become more frequent as temperature rises and rainfall becomes more irregular. And they've estimated that by 2070, there will be a several-fold increase in the rate at which the virus spills over to individuals that are at risk, and particularly in these worst-case scenarios or higher-risk areas that don't necessarily or haven't necessarily planned for this. Similarly, this is a study that looked at hantavirus, and they, again, tried to model sort of climate change. They also, interestingly, looked at sugarcane expansion around in the US, but also in other areas of the world. They found that, they kind of comment on the fact that there have been studies specifically in the US that have associated the population of the rodent hosts with the prevalence of disease and precipitation. And so what they found in this study is that temperature anomalies over time seems to increase the risk of not only hantavirus transmission, but also the risk of hantavirus cardiopulmonary syndrome, up to 34% higher for individuals that may already be at risk. And the reason for this is that the temperature changes may affect, I think I mentioned earlier, may affect rodent populations, right? Vegetation may attract more rodents to come together in smaller density areas, which would then allow for proliferation and potential onward transmission of the disease. Okay, so that was sort of an overview of what we know about zoonoses, zoonotic viruses, zoonotic pathogens rather, and climate change. So I want to move over to vector-borne diseases, which is a whole new and complicated area of its own when we think about its relationship and associations with extreme weather events and climate change. So as we all know, vector-borne disease, very common, account for more than 17% of all infectious diseases worldwide, are estimated to cause over 1 million deaths annually. Malaria really has the burden of this, with over 600,000 deaths, and this was in 2017, so there have been some updated numbers since then, followed by dengue. But malaria far outweighs most of the other vector-borne diseases. And I think one thing to note here, again, as many of us probably know, is that the issue with vector-borne diseases is once it's introduced into different settings or settings outside of where it may be endemic, these infections can be explosive in terms of their development into outbreaks or epidemics. So think Zika, for example. And we've seen that over the past 3 decades, vector-borne diseases have really, in fact, experienced resurgence and reemergence in prior or new geographic locations. But the drivers behind this are pretty complex. And so we've talked a little bit about global travel and trade, urbanization, land use changes again, behavioral practices. I've put deterioration of public health surveillance. I know I'm preaching to the choir here, but I'll talk to you a little bit about, we're going to talk about malaria and really think about, again, this adage where public health is, when it's working well, we don't know it's working, but once you pull back those resources, of course, we start to see resurgence and reemergence of those infections. But lastly, one of the other positive drivers here are ecological complexities and changing environments. But we're going to see that this is actually complicated, and it really depends on the vector, and it depends on the infection as well. So what are the pathways between climate change and vector-borne disease? This is a good review. You can kind of see it. This is in the New England Journal a few years ago, and they talked about how rising levels of CO2 and other greenhouse gases lead to warming of the global atmosphere, which leads to changes in precipitation. You might see areas of increased flooding when areas where there's increased drought. And ultimately, if you go downstream from that, this has a wide variety of effects on pathogens, on the vectors, and also on the hosts. And this is why it's very difficult, I think, to predict in what way vector-borne diseases are going to ultimately be affected by extreme weather events. This is evidence of what's been ongoing, though, when we look at malaria and dengue cases and deaths and annual mean land temperature. So this is between 1993 and 2013. So you can see here, even here, there are areas that have seen explosive growth in these cases related specifically to mean land temperature change, but there are areas that have seen subsequent decrease in incidence. And so I think trying to really quantify exactly which way this is going to go is challenging. This is the last terrible slide I have, I promise. This is just a table that I love because they really try to summarize what the Intergovernmental Panel on Climate Change reported with relation to arthropod-borne diseases. And this commission came together, and they reported, this was several years ago at this point, but they had high confidence that vector-borne diseases in general have increased globally. And they were specifically really called out, there are many here that they've called out, but specific ones that they were concerned about that we may see explosive outbreaks related to climate change were dengue, Lyme disease, and West Nile virus, actually. But again, they conclude that the interactions between temperature, vector survival, and feeding behavior are complex, and that's why it sometimes is challenging to try to really parse out what these associations are. And so, I think I've been saying this over and over again, but I think, when we think about VBDs, a lot of the effects on transmission are nonlinear with relation to climate, and they can act in opposing directions. So higher temperatures can increase vector biting rates, vector development rates, and pathogen replication in certain cases. However, higher temperatures can also result in decreased vector survival in certain areas, particularly if associated with moisture stress. And I think that's why it's been so hard to get really good predictive analytics on this. And again, vector-borne diseases also, we've seen that they're highly sensitive to other human behaviors outside of just climate. So again, urbanization, land use changes, improved healthcare access may actually have improved our ability, right, to detect and also to care for patients, and therefore prevent onward transmission. But also areas with higher population density and poor sanitation that can increase risk. And then, of course, global transit. So again, pretty complicated. But if we think about a case study here, I think this is a pretty good one, thinking about malaria. So in 2023, CDPH confirmed 157 cases of malaria in California. 156 of these patients reported compatible travel history to malaria endemic areas. And so generally speaking, right, when we think about malaria in the US, we think of these as primarily imported or among individuals who were visiting or traveling to a place where malaria is endemic, and then they come back and then present with symptoms. However, if you guys remember in the news a couple of years ago, there were a few cases in Florida and in Texas as well, where local malaria transmission was reported. So these were autochthonous cases among individuals that didn't have any compatible travel history or known interaction with anyone that had had a compatible travel history to suggest that that was the route of where they had acquired the infection. And so this, of course, takes us back to good old public health. So if we think about malaria in the US, it was previously considered endemic in temperate regions. But in the 1950s, malaria was nearly eliminated from the US, really through some really fantastic efforts through the US Public Health Service. These are a couple of images. These were, I believe, actually posters from 1920, where they really focused on vector control strategies. And so since that time, malaria cases in the US, as I mentioned, have primarily been imported. However, sporadically, we do get reports of cases of locally acquired infections. And the reason for this, again, multifactorial, but we know that the Anopheles mosquito vector is still present in parts of the US. And so given the right conditions, reintroduction of malaria to previous endemic areas with potential limited local transmission is expected. And so this is to say that, there's always the possibility that this could occur. However, it's also very likely that climate changes and warming temperatures in certain regions have contributed potentially because you have the right sort of environment for the vector to be able to proliferate and cause onward disease transmission. And so this is actually a paper from PNAS in 2014. This was a projection that tried to really quantify the impacts of climate change on the global distribution of malaria. And so you can see it gets a little bit complicated, but essentially what the authors look at is the length of transmission season. And they found that as this season decreased over South America, right from into the 2080s, so this is a 60-year period, that the models that they developed simulated a shift from malaria being endemic in areas to epidemic transmission over this region. But they found that there were other areas, particularly over the African highlands, where warming temperatures could lead to an increasingly suitable environment for transmission. And so, again, I think the kind of conclusion here is that climate change may increase opportunities for malaria transmission in traditionally malarious areas. In areas the disease has been controlled, as well as in new areas that are traditionally have been non-malarious, but that potentially it could go the other direction as well, just depending on the environment. And of course, we have to consider what vector control strategies are being implemented, and mitigation strategies are being implemented as well. Okay, so another vector-borne disease, Lyme disease. I know we all love Lyme disease. So this is, was in 2023 the most commonly reported tick-borne disease in California. And if we look at potential associations with climate change and Lyme disease, so again, another projection, but this study looked at Lyme disease incidence using climate and land cover by US county. And what they found was, and this image is trying to show the change in case counts of infection based on varying degrees of climate change-related scenarios. So they really simulated different effects, potentially, of how temperatures could warm in certain regions versus others. And they found that the relationship between climate variables and Lyme disease incidence really varied based on geographic region, but that the strongest climate disease association observed between warming temperatures and increasing incidence was in the Northeast, which is, of course, that's where I train. We saw tons of Lyme disease and other tick-borne illnesses. And so I think that kind of makes sense. But they also found that overall, climate actually explained less variation in incidence in other areas of the US as compared to unobserved county-specific heterogeneity. So again, there's probably lots of factors that will likely influence sort of the trajectory of Lyme disease incidence in the future. And then I really wanted to talk about one other vector-borne disease, so Oropouche virus disease. folks heard about? I'm sure you have. Okay. So we know that from late 2023 to 2024, there were outbreaks of Oropouche virus disease in several countries in South America and the Caribbean. So for those of you who may not be as familiar, this is a arbovirus, first isolated in Trinidad in the 1950s from a forest worker. Since that time, several outbreaks have been reported in areas of Central and South America, specifically around the Amazon basin. The thing that's unique about Oropouche virus is that it has a tri-segmented genome. This is important because it's prone to reassortment, and so this allows for potential future emergence of novel viruses, particularly when co-infection occurs with genetically similar viruses. And this has already been observed. There are 3, actually, sort of iterations of this that have been observed in Central and South America. And so when we think about sort of viral transmission and distribution, this is maintained by vector-borne transmission. There are 2 cycles, a sylvatic cycle that can spill over into humans, and then establish urban transmission cycles. And this is where you see these explosive outbreaks that occur. There are a few different hypothesized or known vectors, and the reservoir is this very cute-looking sloth. This is hypothesized. We don't know for sure. It's the 2- and 3-fingered sloth. The distribution of where they live seems to align pretty well with the known area of endemicity for Oropouche virus. But it's also been hypothesized that there are other non-human primates and bird species that are the reservoir. So what's unique about this recent outbreak in the summer and fall of 2023-2024, it's that while prior outbreaks were primarily, again, in the Amazon region, there were not only an increase in number of cases in general, but there was a detection of cases in new regions outside of known areas of endemicity. So countries including Cuba and Bolivia. And then, the reason that this sort of came up and became of interest in the US is there were many cases that were reported related to travel to Cuba in the United States and also in Western Europe. Now, the way this presents is very similar to many of the other arboviruses, which also makes it a little bit tricky to identify, right? Where you have an acute febrile illness, you can get headaches, myalgias, arthralgias. However, the other thing that was unique about this particular outbreak were that there were 2 cases of fatalities reported among young females. And there were also, I don't think I put this in the slide, but there were also cases where there was potential concern for vertical transmission as well. And so, of course, there was, people were worried that this might be another sort of situation similar to Zika, but sort of ongoing investigations have been occurring for that particular component. This is from 2024, but there were about 100 cases during this time period that were ultimately detected in the US. Again, all of the cases were travel-related. But of course, the question became, well, why are we seeing this virus pop up in areas outside of traditional regions of endemicity? Again, multifactorial. One other thing that we haven't mentioned is we also have improved surveillance methods. And so we're testing more, and particularly in regions of endemicity. And so that might also be one reason. However, this study actually tried to look at the transmission risk of Oropouche across the Americas, and again, looked at climate specifically. And so with these models, and this is kind of going from left to right here, they found that there are certain climate factors that may have actually increased the suitability for this infection to be able to transmit more efficiently. And that may be one of the reasons why we're seeing this expansion. Okay, lastly, I'm going to speed through fungal infections, although there's a lot of interesting notes to say here. So within the past decade, we have been seeing fungi and fungal diseases in areas, again, outside of historical regions of endemicity, and also seeing fungal infections attributed to fungi that were not particularly or previously considered to be pathogenic. And folks, mycologists and other folks have posited that maybe climate change is one reason why. Now, how would this occur? So we talked about how fungi are uniquely sensitive to temperature shifts. And warm temperatures may help with fungal dispersion in certain cases, but warmer temperatures may also contribute to evolving heat tolerance and adaptation among certain fungi, which make it easier for endemic mycoses to set up shop, but also to spread. And so this is a nice paper that actually looked at coccidiomycosis, which we all know it's a fungal infection caused by the inhalation of spores of the soil, from the soil, and it can become airborne through wind erosion or soil disturbance. And this study looked at census tract level surveillance data from 2020 to 2000 rather to 2020 in the western U.S., which is primarily where we see cases here. And they found that multi-year cycles of dry conditions followed by wet winters seem to actually increase the transmission risk of coccidiomycosis. And so, the authors conclude that with sort of broader climate shifts, we may end up seeing increased cases and also, again, wider ranges of endemicity. One potential pathway is dust storms, wildfires. This is currently being investigated and has been investigated, particularly if you recall, after, I believe it was in 2020 when we had the really bad wildfires here in the region, we started to see increased cases, actually, of coccidiomycosis. So, of course, these are all observational studies, but we did see that increased incidence, and so this is one potential way in which we may see effects on this particular fungi. I know there was a great talk that talked about C. auris just before the break, and so climate change and extreme weather events have also been implicated actually in the emergence of C. auris. So we know that C. auris appeared simultaneously across 3 different continents, 3 different clades. However, the isolates were genetically distinct. And so this is from a paper in 2019, and the authors talk about how mammalian resistance to invasive fungal infection and fungal diseases is proposed really from a combination, or proposed to result from a combination of high basal temperatures in humans, which create a thermal restriction zone, and also advanced host defense mechanisms in the form of adaptive and innate immunity. And so with warmer climates, there's a concern that the magnitude of the gradient between ambient temperatures and mammalian base temperatures will actually decrease, and that's what would select for more thermally tolerant fungal lineages. And so this is sort of one way in which C. auris may have actually emerged, is that thermotolerant C. auris may have been transplanted by birds across the world to rural areas where humans and birds are in constant contact. And then, that set up the pathway for interspecies transmission, that selected for more virulent for virulent pathogens, virulent C. auris rather. And then that, of course, moved to urban areas with human migration. So this is all speculative, of course, and we definitely need further studies to try to establish this pathway, but I think it's sort of a compelling argument for, one, how this may have emerged, but two, thinking about sort of the dispersion of endemic mycosis in general, and also the emergence of novel fungi in the future. Okay. So that's all I've got, but I think I just want to conclude here by saying, if I haven't really hammered it in enough, is that the effects of climate change and extreme weather events on infectious disease epidemiology, it's multifactorial and it's variable. And I think we're still trying to understand kind of what direction this is going to go. And as you've seen, predicting and projecting these effects it's complicated, it's challenging. But I think the one thing I take away from all of this is certainly we need to think about mitigation strategies. Certainly, familiarize ourselves with pathogens which may not be historically in our regions of work and care, and of course, thinking about equity-centered approaches for mitigation in the future. I'm happy to take any questions if we have time, and thank you so much.
Hi, I just wanted to say thank you. That was a great talk, a great overview. Hi, over here, I'm Grace from Stanford Medical Center. So I just 2 comments about, one, Lyme disease. It's really traveling northward now, and apparently it's in Canada, where the Canadians don't really know how to deal with it the way we have known how to deal with it on the East Coast of the U.S. for many years, where I trained, so I've seen a lot of Lyme in my day. But so that's one thing. I mean, and the other thing is how coccidiomycosis is moving east from California and our valley area, and the bottom line is, I don't know. I think we just have to take vectors and changing vectors and what they carry more seriously. People never really cared about getting mosquito bites other than that it was a pain in the neck and itchy. But, now there are really serious diseases. And when there was, I think, a case of malaria in Maryland also that was, not imported. And so, because the Anopheles mosquito can live there. So wherever it lives, there are the potential for these diseases. And I think we as humans have to adapt. We have to, I know people hate to use chemicals. They don't want to put, and I'm not trying to promote them, but at the same time, you have to do the risk versus benefit. And I do think permethrining your clothes outside, letting them dry, and then having them, be protected if you're going to be wearing them out in the woods. We need to be in nature. But we also will therefore be exposed to mosquitoes and ticks and, everything that carries disease, including the mites. And so bottom line, I think this is really important information, and we have to understand it so that we can adapt ourselves and survive. Thank you.
Thanks for that comment. Yeah, great. Agreed.
Hi, thank you. That was a great talk. I was wondering if you could talk a little bit about the different vaccines, that we have for dengue, the dengue vaccine, and when it's appropriate, and then also if you could talk about the chikungunya vaccine. I think one of them was pulled out recently, so I think there's only one left.
Yeah.
But I don't think it covers all of the age groups, right? So I think that's an issue. So can you talk a little bit about the vaccines?
Yeah, I mean, it's tough because, mostly, those vaccines have been used really cases for travel. So there's not necessarily something that was even recommended to be giving, broadly speaking, to communities here necessarily. And I will say that the vaccine landscape is rapidly changing and evolving, and so I think. I don't know. There's not too much to say other than I think there are certainly promising candidates. There's certainly some issues, as you mentioned, with the chick vaccine, which is why it was pulled, and some with regards to some post-marketing surveillance that occurred there. I think in terms of thinking about people that may be at risk, certainly I think that's still where we focus. In terms of who's going to get them. I don't see in the foreseeable future that we would be giving them to everybody yet. But certainly, right, I think that was a perfect comment that these are things that we need to be aware of because potentially we do have the vectors for a lot of these infections, including for dengue and chikungunya. And so there's always the possibility that we will need to deploy them. I don't know if I answered that question very well, but okay, great. There's a lot more that could be said.
There's going to be an ACIP meeting, I believe, in October, where they're going to discuss chikungunya vaccines in general. What I wanted to mention is that the live attenuated vaccine is the one that was on the 22nd of August had its BLA revoked, and the virus-like particle one from Bavarian Nordic is still FDA approved.
Yep, thank you. They were just asking if you could repeat that, because yeah.
Repeat the whole thing? Okay.
Maybe the Cliff Notes version.
So there were up until recently 2 chikungunya vaccines that were FDA approved. One was from Valneva. It was a live attenuated vaccine. This was for 18 years of age and up. And there were some safety concerns actually in May. So there was actually, and the concerns were around elderly, 65 plus. It was cardiologic and neurological SAEs. Yeah. So it was halted. And then actually on the 22nd of August, so like 2.5 weeks ago, there were more reports globally on some SAEs and some fatalities. So it was actually, the BLA was revoked. The other vaccine is from Bavarian Nordic. This is a virus-like particle vaccine, so it's actually based on a chikungunya virus-like particle. It's non-replicative because it doesn't have any RNA material inside the actual particle itself, and it's approved for 12 years of age and up.
So I have a question. Thank you very much, Dr. Desai. I'm right here. Thank you. That was a great presentation, very clear. I'm looking forward to looking at your slides. All those tables and the references were perfect. So
A very small font, yeah.
they were perfect, and it's, you know, like we need to look at those tables and slides and references because when we're trying to address climate change, those are things that we need to address now and in the future. So thank you very much. So I have a question for you. So what do you think that a premier medical school and veterinary school like UC Davis and University of California, what's the role of the University of California and again UC Davis in informing or advocating regarding climate change policies in California? Because your slides are really compelling of multiple viruses. You explained the vectors and hosts processes and how they've changed well. So those are just like two-part question. What do you think should be the role of your institution and University of California, and what should be the role of us in public health and healthcare locally to advocate for climate change?
Thanks so much. Those are good questions. So I'll say that I'm going to speak as myself and not necessarily on the behalf of University of California, University of California, Davis. But I think in general, you know, a lot of the great work that's come out of some of these studies have come out of academic institutions being able to pull together sort of multidisciplinary teams, because these are really multidisciplinary issues, right? You know, no one department division is going to be able to address the issue. And so certainly I think generating this kind of research and really trying to generate research that goes beyond being merely speculative. As I said, a lot of this relies on predictive modeling, and you kind of have to because you're trying to project what's going to happen. But I think you know, certainly, you know, academia rather, institutions, and particularly institutions that have both, you know, a veterinary school or an agricultural school or medical school, you know, all of these working together. I mean, this perfectly encompasses the One Health approach. That's what you need for this. So, you know, the role of documenting through, you know, robust research, certainly. And I think the role, you know, another role of an academic institution is certainly to advocate based off of this research. That can get tricky. And so, you know, in terms of our public health partners, just generating awareness based off of all the research that's been done is important, because at this point, I think it's really about trying to mitigate and adapt. Not even mitigate, really, adapt, right, to the changes that have already occurred. And I think, you know, the thing that I find really interesting, and I think, I think our colleague who talked about Lyme disease in Canada, for example, it's a great example where we have an opportunity to be able to educate our fellow, obviously, the populations that we serve, but also our fellow clinicians and public health practitioners on understanding that you may be seeing more of these particular infections that we may have experience with, but other places may not, to be able to better prepare them and to be able to communicate the risks in a way that can inform the public as well. I would say those are sort of the two main things. Maybe not so creative, but I feel like that's you know, those are important roles for both of us, and also to partner together, honestly, because they're obviously both components have, you know, like for example, for us, we work really closely with our public health partners, and it's very important because we have the ability to reach different populations, but also have different skill sets that are very complementary to one another to try to get the information out there. Thank you.
Two questions. Thank you. I'm Chris. One is, I haven't seen much talk about the role of industry and private, corporate industry and food agriculture and their contributions and responsibilities on this subject.
Yeah.
And second, I just want to address the gap between communication and adult learning styles and how it has shifted immensely so that we are not really dependent on, learning in this environment as a collective society. Like, young people are really, I say young people because I'm not really one of them, but are really engaged in a totally different way of learning. So how can this be applied in an educational way to contradict some of the misleading dis and misinformation that's prevalent in the scrolling universe?
Yeah. Oh, these are all great questions, and these are big societal questions and issues too, right? But I think the point about engaging industry and agriculture is really important. And actually, in fact, myself and some of my colleagues at UC Davis are doing some work kind of in that vein, specifically related to fungi and certain endemic mycoses and antifungal resistance, actually. And I think the main issue is, right, we've all been in silos for a long time, and but again, all of these issues, they work together, and so there were at least, previously there were efforts to actually try to bring a lot of these voices together, and including people from industry, including people that represent, folks in agriculture, to talk about, right, like, obviously we need to find ways to come to an approach that is going to protect our crops and protect our ability to have, food sources and the economic concerns, but also protect public health down the road, try to better understand, how potential human behaviors might affect or impact, right, antifungal resistance or antibiotic resistance, et cetera. And so I think trying to bring those people together in the same room, and also from the sort of governmental side as well, is very important. So I would say that I think there are folks that are aware of this and want to try to bring everybody together to the table to talk about this. Obviously, there's so many factors that make it challenging, but I think there's an increased recognition that this is important. And then in terms of combating misinformation and disinformation, and I got to answer this in like 1 minute. Okay, let me see. So I would say that I think that there are a lot of folks that appreciate if we talk about extreme weather and climate change, right, they appreciate the really gravity of the situation and all of the potential concerning downstream effects. How to leverage this against misinformation and disinformation that's floating around there, very difficult. I'll say there's a whole body of literature that looks at this outside of the climate change discourse, but in other sort of public health interventions like vaccines. And one thing that is consistently, and actually I can point you to the Vaccine Confidence Project. They're out of the London School of Tropical Medicine and Hygiene. They've done a lot of work in this area and trying to understand how do we, one, kind of like what's going on with misinformation, disinformation, and two, like what are the best interventions? And one thing that consistently comes out is having trusted messengers, even for different generations, folks that people really connect with and trust on a level outside of these issues, to be able to advocate for, science and for putting out the right information. There's some great YouTubers out there even, I would say. Obviously that can be a black rabbit hole, but there are some great folks out there that have clinical backgrounds, public health backgrounds, that are really trying to attempt to engage these younger audiences on platforms that are more relevant to them, to try to combat this kind of misinformation, disinformation. And that's kind of, that's what's been found to work in the past. Now, whether that's enough, with kind of how this technological space is evolving, remains to be seen, and we may have to think of other methods to engage people. I guess the second one, alongside trusted messengers, is engaging communities too, right? So people are more likely to trust their neighbor than they are potentially somebody outside of their community. So just because of the pre-existing relationship. And so trying to find folks like within a community that are willing to be advocates, I think goes a long way too. Tough questions though. Thank you. Should I give this back? There. Oh, okay, great. Do you have a Mac?
I have, but I don't think I need.
Oh,
I just
no,
need the
this-
regular guy.
Oh, okay, then you can just push
Yeah.
that.
Is this yours? Or no?
No, that was
Okay.
our friend,
Madeline.
our friend back there.
Yeah, okay, thank you.
Thank you so much. I appreciate it.
Okay, let me get 1 second. Thank you, Dr. Desai. That was a great talk. We just had a request to speak in the microphone.
Sure. I was just trying to figure.
No, I know. All right, we're doing okay. So I'm going to try to speak on the microphone. All right. So I'd like to introduce our last speaker of the day, Dr. Jagannath. He comes to us from UCSF, and he's going to talk to us about a super important topic. He's going to talk to us about the prevention, the diagnosis, and the management of TB in children. Dr. Jagannath?